Let's pick up right where we left off with the last lecture. We were talking about the ideal gas law and some adjustments to the ideal gas law. So the van der Waals equation applies some adjustments to the equation. Notice again we have this the additive effect onto the pressure and a subtractive onto the volume. Let me just write some of these factors down as to why. And all these gases have their own independent values. So if I had a chart, I would find two sets of values, A and B, for each individual gas. So it's not just like a general idea. Each individual gas has its own A and B values. So A accounts for attractive forces, and B accounts for the volume of real gases. And I'm just squeezing this in here. Both of these values increase with molar mass. So in other words, with the higher molar mass, you get more attraction because of London dispersion forces, and they individually take up more space. So that's leaving that part off. Okay, let's move on and do a couple of homework problems. I think we're on 77. We'll just finish these up as a matter of fact. For number 77, what change or changes in the state of a gas bring about each of the following effects? The number of impacts per unit of time on a given container will increase. So this may not work for every single one, but we'll just take a look at using Pivnert as a tool. So using some of these, which will give us larger impacts. Well, if you increase the temperature, then you're going to add faster particles. They're going to move more quickly with more energy, and that is something that's going to make more collisions. So temperature is something definitely that's going to work. Temp. The pressure in the container. If the container it has higher pressure, the volume's the same, therefore I have more stuff in the container, the moles went up, then therefore you're going to have more stuff around, there are more collisions. So we'll say pressure, and I'm not going to write this down, but as a result of adding more stuff, gas, to the container. So pressure increases. And then the last one is a volume decrease. So if I keep the same amount of stuff, but in a smaller space, they're going to run into each other more frequently. So all of those will increase the pressure or increase the number of collisions. Number of impacts per time on a given container wall increases. Okay. B, the average energy. As soon as I hear that, I'm pretty much done, but I'll finish reading. The average energy of impact of molecules with the wall of the container decreases. Whenever you hear the word energy, that translates to one thing, temperature. So if I wanted to decrease, then we simply will decrease the temp. Done. The distance between the particles increases. This kind of goes back into the same thing we were talking about with C. So if I want the distance to increase, I need a larger container. Therefore, increase the volume of the container. And the average distance between them, I could also decrease the pressure. And this is, again, a result of taking stuff out of the container. That's the only way that's going to happen if you're just discussing pressure. So I have to remove some of the moles of gas from that container, and therefore there's less in there. They run into each other less frequently. The average speed of the molecules in the gas mixture is increased. Again, you hear about speed, you think about energy. That is going to be temperature. Increase the temp. Problem Done. 93. 93 is a pretty good question. List 2 experimental conditions under which gases deviate from ideal gas behavior. Sounds like we just talked about that just a few minutes ago. Well, at high pressure, you force these particles into closer proximity with each other, and therefore they're going to interact. And if there are attractive forces, that will lower the pressure from what you would expect to be ideal conditions. That's one, at high pressure and low temp. As the temperature decreases, the same thing. The energetic collisions are reduced, therefore they're going to be in closer proximity more frequently, and they're going to interact with potential attractive forces. List 2 reasons why gases deviate from ideal behavior. So we kind of talked about that. And I'm going to just be really simple with this, and I'm going to say 2 reasons why. Attractive forces. Two reasons why they deviate from ideal here. Attractive forces and volumes. I'll just say real volumes. So according to the kinetic molecular theory, we like to assume they have no volume at all, but we know that's not true. They do have real volumes. They do interact. Okay, really good one here. Explain how this function can be used to show how gases behave non-ideally. Well, to finish this off, all of this here is equal to N using Pibnert. And how many moles are in the ideal gas equation if you're talking about like the R value? It is 1 mole. So therefore, if I'm doing some math here and I get a number that is larger than 1 or smaller than 1, I can see how these interactions are taking place. For example, if the value, I'll go ahead and write this down. 1 mole at ideal conditions. If the value is greater than 1, then molecules are, and again, this is relative, are taking up extra or more than anticipated space. And it needs to be corrected by that whole negative NB. If the value is less than 1, then there are attractive forces. And it has to be corrected with that additive value. Okay, that one is done. Let's move on over to some notes. Last little bit here, we are talking about, get this in position, grams law of effusion. So I'll get started on this and then eventually we'll have to put it on to another lecture. First, at a given temp, all gases have the same kinetic energy. So any two gases that are at the exact same temperature, they have the same kinetic energy. And kinetic energy, going back to an equation you probably learned back in middle school once upon a time, kinetic energy is 1/2 mv squared. Easy enough. Okay. Then, if the kinetic energy is equal. Then the smaller, and we'll interpret that as being lighter, less massive particles have larger, and we're going to call those speeds. There's a more fancy way of talking about that, but we're not going to do that right now. We'll just say speeds. All right, let me break right here, and then we'll start up again on the new lecture.